Topic 1.2, Logarithm Laws. Here are some timestamps. Now, let's look at the logarithm of a non-positive number. Let's suppose this was defined. Let's say defined as log a of x equals to b. Now, we're going to prove why this is not defined if x is less than or equal to 0. So, by definition, we can define this as a to the power b equals to x. And what's interesting is that if this is an exponential function, it has to be greater than 0 for exponential functions. That's by definition. So if it's not greater than 0, we can state that the exponential function does not exist. And since a logarithm is logarithmic function is the inverse of an exponential function, we know that it will not exist if there's no exponential function. These ones are pretty simple. A to the power 0 equals to 1. We know that a is defined in real numbers and is greater than 0, cannot equal to 1. We know this is the case, this will exist. We know this is just a to the power 1 equals to a, just by definition. And for this, we have our base and our logarithm equals our anti-logarithm. So we know that a of k equals just a of k. For this one, it's really interesting. We know that this produces the logarithm of base a and anti-logarithm of k. Which means this is our anti-logarithm, this is our base, this is our logarithm. So this is just an identity and it will always hold true. It's a bit hard to wrap your head around, but it works. Now let's look at the power rule of logarithms. Let's suppose that we have just m equals a log a of x, which means x equals a power of m. We know that x to the power of k, let's say raise both to the power of k, where k is some real number, not equal to 0. We could state that it's going to be a k. Now, if we log both sides of a, we get a k, which we know, using this inverse property of the logarithm, we can just state that this is just mk, which we can get down to log a of x times k. This is really interesting. This is the power rule of logarithms, and it's really useful for proving some stuff we're going to work with later. So for this one, let's suppose that x equals a log a of m, and suppose y equals log a of n. So what's interesting is that m equals the a of x, and n equals a of y. Mn is going to be equal to ax, ay. Now let's say we log a both sides. We're going to get log a, mn equals log a, and then this is a, but because we can combine these exponents, we're going to get x plus y. And by using the power of these properties, we could just state that this is going to be x plus y, which is log a of m plus log a of n. It's a pretty simple proof and it works pretty well. The difference rule is really simple. It's pretty much the same thing, except instead of x plus y here, it's going to be x minus y, or you can use any parameter you want, but anyways, it's going to be x minus y. So it's a pretty good exercise if you wanted to try it yourself. Now let's look at the base switch rule. Let's suppose let x equals a log a of b, such that ax equals to b. And we know if we divide both exponents by x, we're going to get a, x over x equals b, 1 over x, which is just a equals b 1 over x. If we log b both sides, let's say log b, a equals log b, b 1 over x. What's interesting is that we end up getting 1 over x here. If we isolate for x, we're going to get x equals 1 over log b over a, which we know x is log a of b. So we know this property holds. We can switch the bases and the anti-logarithm, and we just have to turn into a reciprocal. Now, here's the logarithm-based change rule. Let's suppose that we have y equals log k of x. Don't worry, this will come useful later, such that x will be equal to k of y. Now, let's say we divide or we multiply both sides by an arbitrary logarithm with an arbitrary base. Let's say log a of x equals log a ky. We're going to end up getting log a of x equals to y log a of k, which means y equals log a of x over log a of k, which means since y equals log k of x, we know that log k of x equals log a of x over log a of k. Now you can pick any arbitrary base you want, but this is just a property that will hold. So here is a summary of all of our logarithm rules that we have learned today.